Hi everybody, welcome back to the Professors DuBois channel. This is Professor Victoria and Professor Corey, and today we're going to be continuing our discussion of light. And light in particular has energy. And we know this because our plants are growing and we see the light from the sun is reaching us, and we can feel it. We can feel that energy. We're actually getting warmer. So this is what we're going to talk about today is energy of light.
Yeah, and back to those plants. I mean, if a plant does not have light, it will not live. So there must be some energy. This is again, it's macroscopic observation. So what's going on at the molecular level, or the atomic, or the nanoscale? So one of the real early experiments with light that was called the photoelectric effect. And I want to just spend a little time talking about this because it's very interesting. And what scientists found out is if they would shine light on a piece of metal, they could eject an electron from the metal. So there had to be some type of system in place where they could visualize this, and you can see that in your textbook, how this was done exactly. But keeping it real simple here, we like to keep chemistry simple for you guys. So more specifically, they started shining wavelengths of known light, just one particular wavelength of light, and that's what this is showing. And so the metal here in this example is potassium, and you'll notice that the red 700 nanometer. So nanometer, that's the wavelength. So this has a frequency associated with it. This light wouldn't eject an electron, no matter how intense that light was. So they could make it really, really bright. You could leave it on there a long time, and it's like, geez, there's got to be energy here, but no electrons, even over time, even at high intensities. Whereas if I go to the other end, I've got light at 400 nanometers, and that has a frequency associated with it. This would emit an electron even at real low intensity. Likewise, the 550 nanometer light, the green light. So in measuring the speed of these emitted electrons, there was a difference in the speed, and that seems like we could relate that to the energy of the light. So what the conclusion from these experiments was that light has, you can think of light as like a little package of energy, or a bunch of little packets of energy, and they gave this term photon to this little bundle of energy. And what they said was this light must have a elastic collision with the electron, much like if you were shooting pool, and when pool balls collide, the energy can be transferred from one to another. And this kind of made sense, but it wasn't really consistent with the wavelength theory of light. And so you might ask yourself, well, why then, if the red light there at 700 nanometers is made up of packets or photons of energy, why didn't they emit an electron? And the reason is there wasn't enough energy there. They weren't strong enough. So imagine being at the bowling alley, and your packet, your photon, is the bowling ball. Well, red light, the bowling ball, the photon for red light is like using a ping pong ball. And you could roll 100 at a time, really ramp up the intensity, but you're just not going to have any success in knocking down the pins. With more energy in that bowling ball, we have enough energy to eject the electron. So why is all this important? Again, so we're using these macroscopic observations, and we're going to tie this back to ultimately the structure of an atom. But for now, what we know is light has this property that's rather interesting, because this idea of a photon is not consistent with a wavelength. It's more consistent with light being a particle.
Yeah, or a quantum. we call it a quantum of energy. So you've got this wave-particle duality, and that actually exists for everything. All matter has a wavelength, and all moving matter has a wavelength. And this moving waves here also is behaving like a particle. And that's really interesting and kind of above the scale, the scope of this course. But we can calculate the energy of this photon. So the energy of the photon is a constant, which is Planck's constant, who came up with this theory of this quantum of energy, times the frequency of the light. The Planck's constant is in joules times seconds, and you may or may not see this per photon, but it's the energy of one photon, so you can have that as per photon. And frequency, again, is in hertz. You may see it like that, or seconds to the -1, or 1 over seconds.
Now remember, there was a relationship between frequency and wavelength, so we could do this based on the wavelength as well. So the speed of light is equal to the frequency times the wavelength. So if we rearrange that equation and solve for the frequency, we could say that the frequency is equal to the speed of light divided by the wavelength. So if we were given the wavelength of light, we could convert it to frequency and use E equals h, Planck's constant, times the frequency, or we could simply rewrite the formula as E for that one photon is equal to h, that's Planck's constant, times the speed of light divided by the wavelength. Did we talk about Planck's constant?
I want to talk about the units of Planck's constant are joules times seconds, and if we multiply that times the speed of light, that's multiplied times meters per second. That cancels seconds. And then if we're dividing by the wavelength, that's divided by meters. And then meters cancel, and we're left with joules. So when you solve this, it's in joules, or joules per photon.
All right, so I was just, I don't know if we gave the value of Planck's constant.
In the last one we did it.
We did? Okay. We'll see it again, if not. So here, we're going to calculate the energy of a single photon of yellow light, and we have a wavelength of 222 nanometers. Is that yellow light? I don't think that's yellow light. How about this? Calculate the energy of a single photon of light with a wavelength of 222 nanometers. Let's keep this accurate. We want to keep it easy, but we also want to keep it accurate.
Right. The next example, I think, is yellow.
So the way we would go about this is we would, take our nanometer value and convert it to meters. So since we have a wavelength, we can use the formula E equals h, that's Planck's constant, times c, speed of light, divided by that wavelength. So Planck's constant here, 6.626 times 10 to the negative 34 joules times seconds. That's a really small number, and this will be provided for you. This is one of those numbers you don't have to memorize, but you will just from using it, like the speed of light, which is also provided. So when we do this calculation, we get a value of 8.95 times 10 to the negative 19th joules in one photon. You'll notice that's a really small number. A photon of light does not carry very much energy.
No, but they multiply. So can you go back one? You have this joules times 4. This is the energy of one photon. Sometimes you get asked, what's the energy of a mole of photons? And then you can just multiply by Avogadro's number. Thank you. Here's our yellow light. 582. So pause the video and give it a try. Calculate the energy of a single photon. This will be in joules.
All right, and it looks like our answer has the incorrect number of sig figs. That should be 3.42 times 10 to the negative 19th, just based on that 582 nanometers.
This is a good time to talk about that. So if you have three sig figs in your this is the only measurement that's provided in the question. We want to round what we get in our calculator to 3. So you'd say, okay, I've got 1, 2, 3. I have to look to the next number to see if my third significant figure has to round up or down. And in this case, it rounds up. And this is in joules per photon.
All right.
Thanks so much.
That wraps up. So far we've looked at the relationship between wavelength and frequency and the speed of light. And in this lecture, we talked about how we can calculate the energy of a single photon. We talked a little bit about the history and the photoelectric effect. So that was all kind of interesting. And stay tuned. Much more to come on light and energy.
Bye-bye.